complex numbers. The imaginary unit I is defined to be the square root of -1, and the definition of the imaginary unit is very important because it really begins our conversation of complex numbers. So the imaginary unit I is defined to be the square root of -1. It follows that I squared then would be -1. So the definition for the imaginary unit I really arises from solving an equation such as x squared equals -1. Notice here that there's no real number that we can square and get a -1. And so that is why we need to define that imaginary unit I. Complex numbers are of the form a plus bi. So you'll notice here that we have a real part, so the a is going to be the real part of your number, and bi is called the imaginary part. Okay, so with numbers, numbers that are real can be real complex or non-real complex. You can have pure imaginary numbers. The bottom line is that all numbers can be written in complex form. So if you had a number like just 2, you can write 2 as 2 plus 0i. So in complex form, that is how you would write 2. 2 has a real part, but it has no imaginary part. You can perform operations on complex numbers, and so we can add, subtract, multiply, and divide complex numbers. So let's look at some examples. 5 minus 11i plus 7 plus 4i. These are both complex numbers. Here and here, we know that because they're written in the form a plus bi. Now we're being asked here to add them. Okay, so to add two complex numbers, we simply add the real parts and add the imaginary parts. So 7 and 5 combine then to give us 12. That's our real number part of the answer. And then we have negative 11i and 4i, which will give us a negative 7i. And that's really all there is to adding complex numbers. Now let's take a look at subtracting. Negative 5 plus I minus negative 11 minus 6i. Subtraction works just like addition, with the exception of distributing the negative sign. So once we distribute that negative, what we're going to have in essence is an addition problem. So we have negative 5 plus I plus 11 plus 6i. So essentially we're taking the opposite of every term in that second parenthesis. So now we're all set to add our real parts and to add our imaginary parts. So negative 5 and 11 will give us 6. And then we have 1i and 6i, which will combine to give us 7i. Okay, so we've learned how to add, how to subtract. Now let's talk about how to multiply complex numbers. Okay, so multiplying complex numbers is just really a matter of distributing. So, for example, if we have 7 minus 3i times negative 2 minus 5i. To multiply those, we're going to distribute. The first thing we want to note is, how do we know that it's multiplication? We know that we're multiplying two complex numbers because we have two parentheses here, two sets of parentheses that are back to back. So there's nothing joining those two complex numbers. So in number 1, we had an addition sign that joined our complex numbers. In number 2, we had a subtraction sign that joined our complex numbers. Here there's nothing in between the two numbers, and it's understood to be multiplication. Okay, so we're multiplying those two complex numbers. So what we're going to do then is just distribute across. Okay, so 7 times negative 2 will give us negative 14. 7 times negative 5i is negative 35i. We'll come back and grab this negative 3i, take it across. We end up with 6i. And then multiplying the last, we end up with positive 15i squared. So now it's just a matter of simplifying. So here we can simplify I squared to be negative 1. So this right here is just a negative 1. And so 15 times negative 1 will give us negative 15. So this whole last term simplifies into negative 15. Now we can combine our real parts. So we combine the negative 14 and the negative 15. That'll give us negative 29. And then we can combine our imaginary parts. So we can combine the negative 35i and the 6i. And that'll give us negative 29i. Okay, and then finally the last operation that we're going to look at is division. Okay, so to divide complex numbers, we here have to use what we call conjugates. So for example, say we have 7 plus 4i divided by 2 minus 5i. So we are dividing two complex numbers here. To divide, again, we're going to use conjugates. Now the conjugate of a plus bi is a minus bi. So a plus bi and a minus bi are conjugates of each other. So you'll notice that the first and last terms are the same. It's just the sign that joins them is different. So here the conjugate of 2 minus 5i is 2 plus 5i. Okay, so we multiply the denominator and also the numerator by that conjugate. And by doing so, that will allow us to remove the imaginary unit from the denominator. Okay, so now we're going to distribute. So in the numerator, we are multiplying 7 plus 4i times 2 plus 5i. In the denominator, we're multiplying 2 minus 5i times 2 plus 5i. And now we just distribute. So in the numerator, 7 times 2 is 14. 7 times 5i is 35i. 4i times 2 is 8i. And then 4 times 5 is 20i squared. Okay, and then in the denominator, we're going to distribute the same way. So 2 times 2 will give us 4. Now we'll notice here when we distribute further that our positive 10i is going to cancel out with the middle there, the negative 10i, essentially eliminating that imaginary unit. And that's really why we use the conjugate. And then finally we have negative 25i squared. And so now we're going to simplify that by combining like terms. Okay, so here I squared is negative 1. So in the numerator we have a negative 20 for that last term. So 14 and negative 20 combines to give us a negative 6. And then 35i and 8i will give us 43i. And in the denominator, we have here negative 25i squared. Since I squared is negative 1, that'll give us a positive 25. We'll add that to the 4 to get 29. Your final answer you want to write in the form a plus bi. So your final answer would be negative 6 over 29 plus 43 over 29i. Here this can't be simplified further, but if you can simplify at this point, you want to do that. Okay, and so we see conjugates pop up when we're solving quadratic equations. That's really when we see these imaginary units. For example, let's say we have 3x squared minus 2x plus 4 equals 0. So here we have a quadratic that is not factorable. So we'll use the quadratic formula, and in doing so, as we simplify, we'll see that we need imaginary units to simplify the radical. So the quadratic formula gives us solutions defined by the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So a is 3, b is negative 2, and c is 4. So we're just going to plug in. So we have the opposite of a negative 2, which is a positive 2, plus or minus the square root of b squared is negative 2 squared, which is 4, minus 4 times a, which is 3, and c, which is 4, all over 2 times a, which is 2 times 3. Okay, and then we'll further simplify. So here we have 2 plus or minus the square root of, then we simplify under this radical, and we'll end up with negative 44 over 6. And here's where these imaginary units come in, because we can't take the square root of a negative and be in the real number system. So we need to simplify the square root of negative 44. So to do that, to take the square root of negative 44, we pull our I out by viewing this as the square root of negative 1 times the square root of 44. So we have I, and then we can simplify. 44 is just 4 times 11, so the square root of 4 is just 2. So we have 2 times the square root of 11. By convention, we put the I behind the 2. So we would write that as 2i times the square root of 11. So we're just going to plug that in here. So we have x equals 2 plus or minus 2i times the square root of 11 all over 6. We are almost done. Now we just divide each piece by 2. So 2 goes into 2 one time, 2 goes into 2 one time here, and 2 goes into 6 3 times here. So our final answer then becomes 1/3 plus or minus I times the square root of 11 all over 3.